Picture this for a second. Really picture it. You go to bed on a normal night. You wake up, you check the date, and the calendar has a gap. Not time flew, not I lost track. I mean the date is literally missing. Your paycheck math gets weird. A birthday slips out of existence. A court clerk stares at the form like it's cursed. And everyone around you just acts like this is fine. And it has happened, cleanly, officially, on purpose. In 1582, during the Gregorian Reform, some places went from Thursday, October 4th, straight to Friday, October 15th. 10 calendar dates deleted to fix a drift problem. 10 days gone. Then, much later, in a world with airlines and smartphones, Samoa jumped the international date line, and at midnight after December 29, 2011, it went straight to December 31st. Friday, December 30th did not exist there. So when I say the day that disappears, I'm not trying to be poetic. Honestly, not today. I'm inviting you into a practical question that sounds simple until you sit with it. Why isn't a day just 24 hours, always, end of story? Why do we get missing days, and why do we also get extra seconds? And why should anyone with deadlines care? Here's the quiet problem. Earth is not a perfect clock, and a day depends on what you measure it against. Relative to the stars, one full rotation is about 23 hours, 56 minutes, 04 seconds, not 24 hours, and that small mismatch is why the sky's schedule slides a bit every night. Relative to the sun, the solar day isn't perfectly steady either, because Earth's orbit and its tilt complicate what noon to noon even means in the real sky. And then we, humans, step in. We smooth it into civil time, time zones, calendars, standards, because we need life to run on something stable. Eventually, our clocks become steadier than the planet itself, so we keep UTC mostly uniform and we patch the mismatch with leap seconds, so UTC stays within plus or minus 0.9 seconds of Earth rotation time, UT1. And that's the story for today. How astronomy, religion, empire, shipping, railroads, and modern physics all grabbed the word day, and how the world keeps negotiating what that word is allowed to mean. So maybe subscribe and tell me where you're watching from and what time it is. I always check the comments, and it's fascinating seeing Sydney at breakfast and Lisbon at bedtime, all at once, all of us wondering about the same mysteries. Let's begin with the part that messes with people's stomach a little. Because it's not abstract and it's not philosophy time. It's the calendar, it's your job, it's your rent, it's your kid's birthday party invite that suddenly looks wrong. Sometimes a society will wake up and the next day on the page is not the next number, it's a jump, a clean cut, like an editor took a knife to the month and said, "We're doing it this way now." And if you think that sounds like a fairy tale, it's not. It's a policy decision, signed, printed, and forced. In October 1582, in places that adopted Pope Gregory XIII's reform immediately, Thursday, October 4 was followed by Friday, October 15. 10 calendar dates were dropped to correct the accumulated drift of the Julian calendar and to restore the timing of the vernal equinox to where the Church wanted it for calculating Easter. It's one of those moments where time turns out to be a public project, and the public has to live with the update whether they like it or not. And then, because Europe is not one machine, you get this long, staggered rollout. Some places switch early, others delay for decades or centuries. So in the historical record, you find these weird seams where two neighbors are living in different calendars, and the same day is labeled differently depending on whose paperwork you're reading. It's not just confusing, It changes contracts, diplomacy, shipping schedules, church feasts, and it forces people to learn a new habit. The label on the day is not a fact of nature, it's an agreement. Now, for an audience in the United States, there's another Missing Days episode that matters because it reaches straight into the American colonial world. Great Britain and its dominions adopted the Gregorian calendar in the 1750s, and in September 1552, Wednesday, September 2 was followed by Thursday, September 14. 11 dates removed, not because anyone wanted to be dramatic, but because by then the gap between Old Style, Julian, and New Style, Gregorian, was 11 days. And Parliament didn't just wave its hands, it wrote the jump into law in plain language. Basically, keep numbering days normally up to the 2nd, and the natural next day shall be called the 14th, omitting the 11 intermediate nominal days. People love the riot story here. Give us our 11 days, and you'll hear it repeated like it's settled fact, but even Britannica treats the riot narrative cautiously and frames it as a story that may be more myth than documented event. What matters for us is simpler and more solid. The dates really were omitted, and the government tried to reduce financial unfairness by shifting rents and quarter days forward so nobody lost an actual term of payment, even if the printed calendar had a hole in it. So that's the older, classic missing day pattern. A calendar reform, a correction, a patch for a long-term drift between a human counting system and the seasons. But missing days aren't only a medieval church and astronomy story, and that's where it gets a little unsettling, because you can do it even now, with satellites overhead, banking software everywhere, and someone literally live streaming the moment their date flips. Samoa did something like that at the end of 2011. It shifted to the other side of the international date line, and the U.S. Department of State's Office of the Geographer puts it plainly. At midnight on December 29, 2011, Samoa and Tokelau moved from the eastern side of the date line to the western side. In everyday terms, the local calendar jumped forward by 1 day, so Thursday, December 29th, was followed by Saturday, December 31st, and Friday, December 30th did not exist there locally. And notice what's different here. This isn't about the seasons drifting over centuries. It's about lining up with trading partners, airline schedules, and business days, modern economic gravity. The day disappears because the map is being negotiated, not because the sky changed. The international date line isn't a physical fence in the ocean, it's a convention, roughly near the 180th meridian, but it bends around political and practical needs. And when a country decides it would rather share weekdays with its main partners, it can, as long as it's willing to swallow the cultural cost of saying, in effect, "Sorry, your Friday's canceled." So before we even touch the physics, we already have two big categories of disappearing days: calendar correction, 1582, 1752, and dateline relocation, Samoa 2011. And here's the move I want you to make with me, gently. Don't treat these as quirky trivia, treat them as stress tests. When you erase a date, you reveal what a society thinks time is for: worship and seasonal order, taxes and rents, shipping containers, supply chains, synchronized work weeks. You can read priorities off a missing day. And if you want a first taste of the physics side, just a taste, start with the simplest shock. Earth does not take 24 hours to rotate once if you measure that rotation against the distant stars. The U.S. Naval Observatory notes that a sidereal day is about 23 hours, 56 minutes, 04 seconds of civil or solar time. That is already enough to break the childish picture most of us carry around, the picture where one spin equals 1 day equals 24 hours, because the sun is not a fixed backdrop. Earth is moving along its orbit while it spins, so to bring the sun back to the same position in the sky, noon to noon, Earth has to rotate a little more than one true rotation relative to the stars, and that extra bit is what stretches the solar day toward 24 hours on average. And even then, solar days are not perfectly uniform across the year. The mean in mean solar time is doing real work smoothing out the messy parts. We're going to unpack all that later, slowly, because it's the heart of why timekeeping becomes a mix of astronomy and bureaucracy. For now, I just want you to sit with the emotional side of it, because history is not just mechanisms, it's what those mechanisms do to people. If your life is organized around tomorrow, and the authorities announce there is no tomorrow on the calendar, it forces a weird mental flip. You realize you've been using a tool that felt like nature. Even in 1752, the British legislation had to think about injustice and financial hardship because the lawmakers understood the obvious human fear. If the month loses 11 labels, are workers losing 11 days of wages? Are tenants losing time they paid for? Are deadlines being cheated? So the law tried to specify that terms and payments move forward accordingly, like, no, you still get the full natural term, we're just relabeling the days. In 1582, the reform logic is equally practical in its own context. It's about the calendar drifting relative to the equinox and therefore relative to the ecclesiastical calculations that depend on that seasonal anchor. The 10 days vanished because the system was already out of sync, and the only way to restore the intended alignment was to jump. In Samoa, it's about social synchronization in a global economy. The day vanished because being a day behind your partners is not just cute, it's expensive. It complicates business and travel. It creates a constant friction you have to explain to every outsider. So the government chose friction once in one big gulp instead of forever in small sips. So what does this chapter really do for us, besides making the audience lean forward a bit? It sets the contract for the whole lecture. We are not treating time as a smooth, natural river. We're treating it as a negotiated system, layered on top of natural cycles that are slightly inconvenient. Sometimes the negotiation is about calendars and faith and seasons. Sometimes it's about trade routes and date lines. Sometimes it's about physics and standards bodies. But the theme is consistent. When you ask, what is a day, you're not asking one question, you're asking a bundle of questions, and different eras answer them differently. Next chapter, we're going to define our terms in a way that doesn't kill the mood. Civil day, solar day, sidereal day, and why people keep mixing them up. And once we've got that, the rest of the story, sundials, equation of time, railroads, atomic clocks, starts to feel less like trivia and more like a single long argument about how humans live on a spinning, orbiting, slightly unruly planet. We throw around the word day like it's one clean object, like it came out of a factory, 24 hours, sealed, done. But historically, it's more like a bundle, 3 different meanings taped together, and people keep forgetting the tape is there. First meaning, the civil day, the one on your calendar and on your phone, the one that starts at midnight and is divided into 24 hours by definition, because we decided we needed a stable unit for schedules and records. It's a legal social thing, not a telescope thing, and it's meant to behave. Second meaning, the solar day, the day you get from the sun, noon to noon, when the sun crosses your meridian again. That sounds simple until you actually try to use it, because the sun is the clock turns out to be messy. The sun runs fast some days, slow other days, And if you've ever seen a sundial not match your wristwatch, that's the point. The U.S. Naval Observatory defines apparent solar time using the apparent position of the sun, and that apparent word is doing work. The real sun does not keep a perfectly uniform pace as a time signal through the year. So we invent a helper, mean solar time, basically a smoothed version, a pretend steady sun that moves at an average rate, because humans like steady. The Royal Observatory Greenwich explains the old logic pretty directly. True solar day comes from dividing the true solar day into 24 hours and calling the sun's meridian passage 12. But the catch is the true solar day itself isn't consistent day to day, so the true clock drifts against any uniform clock you build. That difference between the real sun and the mean sun is what people call the equation of time, and we'll treat it as a historical actor later because it quietly shaped navigation, daily routines, and the whole transition from sky time to clock time. Third meaning, the sidereal day, which is the Earth's rotation measured against the distant stars, not against the sun. It's the one spin day, the planet's physical turn relative to the background. The U.S. Naval Observatory puts the headline number on it. The interval tied to a full sidereal cycle is about 23 hours, 56 minutes, 4 seconds of solar civil time. That's the first big slap to intuition, because it means Earth can complete a rotation and still not be back to noon, since while Earth is spinning, it's also moving along its orbit. To face the sun the same way again, it has to rotate a little extra, and that extra is what stretches the solar day toward 24 hours on average. So when someone says a day is 24 hours, what they usually mean is our civil day is defined as 24 hours. And that's fine, that's useful, but it's not the same as Earth rotates once in 24 hours, because it doesn't. And it's not the same as the sun returns to the same position in exactly 24 hours every single day, because it doesn't do that either. And here's where it starts to matter historically. Once you admit those definitions differ, you can see why institutions start picking favorites. Astronomers like sidereal frameworks for pointing at stars. Navigators care about the sky but need tables and averages. Governments and railroads need civil time that doesn't wobble with seasons, and modern tech needs something even steadier than Earth itself. That's how you end up with two official kinds of time living side by side: UTC, an atomic-based broadcast timescale for civil life, and UT1, a measure tied to Earth's rotation. The IERS defines UT1 as Earth rotation-based, basically the rotation angle about Earth's pole, and it distributes UT1 minus UTC so everyone can quantify the mismatch. And because the mismatch grows, we sometimes patch UTC with leap seconds. NIST states the job in one sentence. Leap seconds are used to keep UT1 and UTC within plus minus 0.9 seconds. Civil day is the rule on the clock. Solar day is the sun-based day that needs averaging. Sidereal day is the star-based rotation day. Same word, different anchors, different consequences. Next chapter, we go backward a bit, to the sky as the first clock, sundials, local noon, and why communities used to live inside these definitions without ever writing them down until precision and coordination forced everybody to say out loud what they meant by day. Before there were national time systems, before anyone argued about seconds, Most people lived inside something simpler and also more personal. Local time, your own sun, your own noon, your own bells. Noon was not a number on a screen. It was a moment you could point at, the sun highest, shadows shortest, and the community sort of agreed, yes, this is the middle of the day. Close enough. Move on. The earliest, most obvious tool for that is the sundial. Britannica calls it the earliest type of timekeeping device, and the mechanism is blunt. You read time from the position of a shadow cast by something exposed to the sun. It sounds clean, but it's only clean if you don't ask it to do too much. Sundials don't work at night, they don't work well in bad weather, and even on a perfect sunny day, they don't promise you a uniform clock pace, because a sundial tracks apparent solar time, the real sun as it appears in the sky. Britannica is very direct here. Apparent solar time is measured by direct observation of the sun or by a sundial, while mean solar time is the smoothed version kept by most clocks and watches. The U.S. Naval Observatory makes the same idea more technical but also more useful. It says apparent solar time is what a perfectly constructed and calibrated sundial would read at a location, based on the actual position of the sun, determined by the sun's local hour angle relative to your meridian. That meridian detail matters, because it reminds us apparent solar time is local in a deep way. Change longitude, you change the time. So in everyday life, for a long stretch of history, what time is it really meant what time is it here, not what time is it for the whole country. And people didn't need it to be perfectly uniform, they needed it to be socially workable. This is where the church and the town square enter, not as decoration, but as infrastructure. Communities organized work and prayer around recurring signals, services, markets, meetings, often anchored by the idea of hours, even when no one had a personal clock. In the Christian world, one big framework was the canonical hours, a structured cycle of daily prayer services. Time becomes audible. Time becomes communal. Time becomes something you can follow even if you can't measure it precisely. And then, slowly, you get devices that push beyond watch the sun. Water clocks, clepsydra, are a good example. Clepsydra, as an ancient device for measuring time by the gradual flow of water, with designs that let you read time from a changing water level or from a vessel that fills or empties in a controlled way. Water clocks don't solve everything, but they do something important. They let you keep time when the sun isn't cooperating, at night, indoors, in cloudy weather. After that, another shift arrives, and it's basically loud. Mechanical public clocks in towers. The first clear references to mechanical clocks are large weight-driven machines in towers, turret clocks, and that these early devices struck only the hours, often without hands or a dial. It even suggests monasteries as a likely early setting, with clocks used to toll bells that called monks to prayers. That detail is easy to miss, but it's huge for the way people experience time. An hour becomes something you hear whether you asked for it or not, and hour becomes more real than noon, especially in winter, especially in places where the sun is low and the day is short. But there's a catch, and it's a catch that irritates historians and engineers in the same way. The sun is not a perfectly steady time signal across the year. So if you build a steady mechanical clock and you compare it to a sundial, they will disagree, and not by a tiny amount you can ignore. Royal Museum's Greenwich makes this very plain for general audiences. The sun can be as much as about a quarter of an hour fast or slow compared with a clock keeping mean solar time, which is exactly why sundial time and clock time don't line up day after day. That mismatch is the doorway to the next chapters, because it forces a choice. Do you want time to follow the real sky, even when it speeds up and slows down, or do you want time to be uniform so you can coordinate people and machines? As commerce grows and coordination starts to matter more, the pressure builds toward mean time, standard time, and eventually global standards, none of which erase the sun, but all of which stop letting the sun run the schedule by itself. So if Chapter 1 showed that humans can delete dates, and Chapter 2 showed that day has multiple meanings, this chapter shows the lived origin. Time starts out as local sky observation plus community signals, and then technology slowly flips the relationship. Eventually, the clock becomes the boss, and the sun becomes the thing we correct for. Here's the awkward little secret behind sundials and solar time. The sun is not a steady clock face, not day to day, not across the year, and if you try to live strictly by when the sun says it's noon, you'll drift away from any uniform clock you build. What you need, historically, is a correction term, and that correction is what gets called the equation of time. The U.S. Naval Observatory defines apparent solar time as what a perfectly made sundial would read at a location, tied to the sun's actual position and its local hour angle relative to your meridian. And it frames the equation of time as the difference between apparent solar time and mean solar time, meaning the real sun versus a smoothed, imaginary mean sun that moves at a uniform rate. Mean solar time is basically the compromise humans wanted, a day split into 24 equal hours that don't speed up or slow down just because Earth is having a complicated relationship with its orbit. And Earth is, in fact, having a complicated relationship with its orbit for two big reasons that are simple to name and annoying to live with. The orbit is slightly elliptical, so Earth speeds up near perihelion and slows down near aphelion, and the axis is tilted, so the sun's apparent motion isn't aligned with the celestial equator in a way that makes time by the sun come out uniform on a clock. Put those together, and the difference between true solar time and mean time piles up over weeks, and it can get large enough that ordinary people notice. Royal Observatory Greenwich states the extreme differences range to about 16.5 minutes around November 3rd, true noon ahead of mean noon, and about 14 minutes around February 12th, true noon behind mean noon, which is a polite way of saying your sundial can be off by about a quarter hour even when it's working perfectly. This is why local noon is a slippery hero in the story of timekeeping. It feels natural, it's visible, it's emotionally satisfying, but it does not give you a uniform pace. And once societies start wanting coordination, ships meeting tides, markets opening reliably, later trains not crashing, you see a slow pivot away from the real sun as boss and toward mean time as boss, with the sun becoming something you correct for using tables, almanacs, and later standardized signals. The equation of time also shows up visually as the anelema, that figure 8-ish path you get if you mark the sun's position at the same clock time through the year. It's a reminder you can hang on a wall. The sun doesn't come back to the same clock place in the sky on a neat schedule. So in this chapter, the point is not to memorize a curve, it's to feel the pressure it created. Once you admit there's a systematic seasonal mismatch between sundial time and uniform clock time, you can see why a day starts splitting into kinds: apparent, mean, civil, and why later chapters will keep returning to the same theme. Humans keep building smoother time, then patching it back to the sky when the gap becomes socially or technically uncomfortable. The sidereal day and the 4-minute drift. If you want the cleanest way to see the problem, don't start with calendars. Start with the stars. Stars are basically the fixed background our ancestors trusted and astronomers still trust. A sidereal day is the time Earth needs to rotate once relative to the distant stars, one full turn, 360 degrees. Measured in civil or solar time, it comes out to about 23 hours, 56 minutes, 4 seconds, not 24 hours. That difference is small enough that you can ignore it for cooking pasta, but it's big enough to run your whole night sky if you pay attention. The same star will cross your local meridian about 3 minutes 56 seconds earlier each civil day, which is why week to week the constellations show up earlier in the evening, like the sky is slowly sliding its schedule. And here's the reason, said in the least mystical way possible. While Earth spins, it also moves forward along its orbit around the Sun. So after Earth completes one true rotation relative to the stars, the Sun is not in the same direction yet. To get the Sun back to the same noon position, Earth has to rotate a little extra, and that extra rotation takes roughly 4 more minutes, which is how the mean solar day ends up longer than the sidereal day. You can picture it like this, not fancy, just practical. Imagine you're turning in place while also walking around a lamppost. One full spin relative to the far wall is not the same thing as facing the lamp again, because your walking changed your angle, so you need a tiny bit more turning. That's the whole trick. And the 4 minutes number isn't random trivia. It connects straight to the year. Since the Sun appears to move against the stars by about 360 degrees per year, that's about 1 degree per day, and 1 degree of extra rotation is about 1/360th of a full turn, which is about 1/360th of 24 hours, which lands you right around 4 minutes. So the mismatch is baked into orbital motion, not into sloppy clocks. Now, the part I want you to hold on to, because it will matter later when we talk about precision timekeeping, is this. 24 hours is not the raw rotation period of Earth. It's a solar-based average that includes that extra bit of rotation needed to catch up with the Sun. If you switch reference points, you switch what a day even measures, and the numbers change without anyone cheating. In the next chapter, we'll stay with this idea, but change the target, not stars, but the Sun itself, and we'll see why even solar days aren't perfectly uniform across the year, which is where things get annoying in a very human way. We used the stars to show a simple mismatch. One rotation is not the same thing as noon to noon. Now we stay with the Sun, because this is where people get surprised in a very ordinary way. Even if you define a day as the time from one solar noon to the next, that interval is not perfectly steady across the year. The basic definition is still clean. An apparent solar day is the time between 2 successive transits of the Sun over the same meridian, one sun due south moment to the next. But the length of that interval changes slightly, and the USNO Observatory says it plainly. Some solar days are longer or shorter than 24 hours by as much as about a half minute. That's not math trivia when you live on clock time. It shows up as a pattern people notice without knowing the name. The earliest sunset and the latest sunrise don't land exactly on the winter solstice if you're reading your life by a modern clock. USNO even uses this as a teaching point. For part of the winter stretch, the actual solar days tend to run a bit long, which nudges sunrise and sunset times on the clock in ways that feel counterintuitive. So why does it happen? In plain terms, because the sun's daily motion in our sky is not just Earth spinning in place. Earth is spinning and also moving along its orbit, and that orbit motion piece doesn't behave like a perfectly uniform gear. Add Earth's axial tilt, add a slightly non-circular orbit, and the sun as a clock comes out uneven from week to week. The USNO's equation of time explanation frames it in a way that's easy to use. Apparent solar time is what a perfectly made sundial would read, the real sun. Mean solar time is the smoothed version, based on a fictitious mean sun moving at a uniform rate, and the equation of time is the difference between the two. And then comes the human decision that makes modern life possible. We do not run civil clocks on raw sun time. We run them on the smooth average. USNO says this directly too. Our clocks keep civil time at a uniform rate equal to the solar rate averaged over the whole year, with each day exactly 24 hours long, which is why even a careful sundial won't match your clock except on certain days. So the takeaway is not the sun is unreliable. It's more practical than that. The sun is consistent in the way physics is consistent, and our clocks are consistent in the way standards are consistent, and those are different kinds of consistency. The solar day stretches and shrinks a little, the civil day stays fixed by definition. And that gap, small, steady, always there, is exactly why timekeeping had to become astronomy plus correction tables and eventually global coordination. The day changes because Earth is not spinning in a vacuum, and the biggest long-term reason is tides, raised mainly by the moon, with the sun contributing too, but the moon is the main character here. The core idea is not complicated, it's just easy to underestimate. The moon's gravity raises tidal bulges in Earth's oceans and even in the solid Earth, and because Earth rotates faster than the moon orbits, those bulges don't sit perfectly lined up under the moon. They get carried a bit ahead. Friction resists that motion, and the result is a torque that slowly steals rotational energy from Earth's spin. Britannica describes the basic mechanism in plain terms. Tidal friction keeps the tidal bulge from staying directly under the moon because Earth's rotation carries it forward. And when Earth loses spin, that angular momentum doesn't just vanish, it gets transferred into the moon's orbit, which is why the moon slowly drifts away from us. NASA's Lunar Laser Ranging write-up puts a number on it that people can actually hold. The moon is moving away at about 1.5 inches or 3.8 centimeters per year. This is not ancient guesswork. This is measured with lasers bounced off retroreflectors left on the moon by Apollo-era missions, and the result has been consistent enough to become a standard headline number in public science communication. Now bring it back to the day length. If Earth is losing rotational speed, the day gets longer, slowly. NASA's Goddard Tide and Rotation page calls tidal braking the dominant long-term effect and gives the classic order of magnitude figure, saying the secular change increases the length of day by about 2.3 milliseconds per century. Milliseconds per century sounds cute until you stack centuries, then millennia, and then you remember history is full of millennia. This is why people can use ancient observations, especially eclipses, to back out how Earth's rotation has wandered over long time spans. A Royal Society paper by Stevenson compiles measurements of Earth's rotation from 720 BC and discusses a long-term increase of the mean solar day on the order of milliseconds per century, and it explicitly compares the observed long-term trend with the larger value you'd predict from tidal friction alone, around plus 2.3 milliseconds per century, which tells you right away this is not a perfectly smooth line. There are other effects on top, and the data quality changes over time. So yes, the moon tide story is the big, slow backbone, but the real record is lumpy. Oceans move, atmospheres move, ice moves, Earth's interior shifts, and the exact rate is not one sacred number that never changes. NASA even has a modern example that feels almost rude in how recent it is. A 2024 NASA write-up describes research finding that since about 2000, days have been getting longer by roughly 1.33 milliseconds per 100 years, with the mechanism tied to mass redistribution from accelerated ice melt and sea level changes, basically changing Earth's moment of inertia, like a spinning skater changing posture. That's a different lane than moon tides over millions of years, but it stacks on top of the same basic truth. Earth's rotation is responsive to how mass is arranged and how energy is dissipated. And this is the history angle I want you to keep because it frames everything that comes later. Timekeeping didn't get more precise just because humans got picky. It got more precise because the sky is not perfectly uniform and the planet is not perfectly uniform. And once society started demanding coordination, navigation, then railroads, then radio, then computers, we had to face the fact that the day is a moving target, even if it moves like a snail. Next chapter, we'll zoom in from centuries to much shorter timescales and look at the jitter, how winds, currents, seasons, even earthquakes can nudge the length of day by tiny amounts, fast enough that modern measurement can see it. While we've previously explored the slow, tidal drag that operates on the scale of geological patience, we now zoom in on the jitter, the day-to-day and month-to-month wobble that reveals Earth not as a rigid clock, but as a living system constantly shifting its weight. The core principle is simple, even if the mechanics are fluid. Earth's rotation fluctuates as angular momentum is traded between the solid crust and the moving layers of air, water, and ice, meaning that over periods shorter than a year, the atmosphere essentially acts as the planet's primary driver. On this scale, seasonal weather variations can alter the length of a day by several milliseconds, with massive climate patterns like El Niño acting as a brake that slows our rotation enough to add a full millisecond to our 24-hour cycle, a tiny increment that nonetheless demands the attention of global timekeepers. This relationship is often framed as an atmospheric flywheel, where shifts in wind and pressure fields correlate so tightly with the planet's spin that atmospheric motion accounts for over 90% of our seasonal variations, leaving the oceans and groundwater to play secondary roles through mass redistribution. Even earthquakes join this nervous dance. Though headlines paint them as cataclysmic, their impact on time is measured in mere microseconds, as massive shifts in rock, like the 2011 Japan or 2010 Chile quakes, reposition mass closer to Earth's axis, causing the planet to spin slightly faster in the same way a figure skater speeds up by pulling in their arms. Ultimately, this nervous planet reality forced the modern world to stop treating Earth as its master clock, because in an age of satellites and digital precision, a non-uniform rotation is no longer a philosophical curiosity, but a practical engineering problem that requires advanced tools like very long baseline interferometry to manage, setting the stage for why human calendars have always been a desperate attempt to keep our social time from sliding away from a restless sky. The Gregorian reform sounds from far away like a clean science upgrade, but when you zoom in, it's more like a messy rollout with theology, astronomy, and government paperwork all in the same room. The basic problem was that the Julian calendar's year length was a little too long, so over many centuries the calendar dates drifted relative to the seasons, and by the 1500s the March equinox was showing up earlier than the traditional March 21 anchor used in church calculations, especially for Easter. Pope Gregory XIII's reform in 1582 aimed to restore that seasonal alignment to where the Church wanted it, tied to the spring equinox date associated with the era of the Council of Nicaea, and the surreal implementation step was the blunt one: drop 10 calendar dates in October so the label catches up to the sky. The jump out in plain words: October 4, 1582 was followed by October 15, 1582 in places that adopted immediately, with the missing dates being October 5 through October 14. If you're listening to this as a history audience, pause and really picture what that means socially. You're not changing the weather, you're not changing the harvest, you're changing the numbering system people use to talk about the days they're already living through. So the 10 days aren't time stolen from nature, they're labels removed from the calendar to repair a mismatch that had already grown. But in daily life, it still feels like someone cut pages out of your month. Gregorian calendar entry describes the adjustment as advancing the calendar 10 days after October 4, with the next day reckoned as October 15 to restore the equinox timing. There's also the part people forget because skipping days is flashy and leap year rules are boring, but the boring part is how you stop the drift from happening again. The reform adjusted the leap year pattern so the calendar year better matches the solar year long term, and the papal bull that introduced the change is commonly referred to as Inter Gravissimus, which is also where you see the reform laid out as an order, not a suggestion. Now, here's where the historian brain should kick in. Even if the rule is universal on paper, adoption is not universal in practice. Countries and territories switch to different times, and that means the same day can have different labels in different places, and sometimes even within the same region during the transition period. So archives get tricky, letters get tricky, contracts get tricky, because you have to ask, are we looking at old-style dating or new-style dating? And did the writer mean the civil date in their jurisdiction or the date in their correspondence? France made the transition separately in December, which gives you a quick taste of how staggered and political this was, not just technical. And then there's the human fairness question, the one that always shows up the minute you delete calendar labels. What happens to rents, wages, loan terms, court deadlines, interest, anything that depends on counting days? The reformers understood this problem well enough that the papal bull summary tradition emphasizes that the missing days were not to be counted for certain obligations, meaning the intent was not to cheat people by shortening a term, but to relabel time while preserving the length of an agreement in natural days. That doesn't mean everyone felt calm about it, obviously. It means the reform came with an awareness that timekeeping is not just astronomy, it's also trust. One more point, because it matters for how we connect this chapter to "a day isn't 24 hours." The Gregorian reform is a calendar fix, not a rotation fix. It's dealing with the mismatch between a civil counting system and the seasonal year, not with the fact that Earth's rotation itself wiggles and drifts, but it sets the pattern that will repeat in modern forms, like leap seconds later on. Humans build a standard, nature refuses to be perfectly standard, and then humans patch the standard so society doesn't slide too far away from the sky. When Britain and its empire finally adopted the Gregorian calendar in 1752, it wasn't just a simple date change, but a massive administrative upheaval consisting of two radical shifts layered on top of each other. First, the government moved the legal start of the year from March 25th, the traditional Lady Day, to January 1st, a move that disrupted centuries of contracts, court terms, and economic cycles built around that old spring boundary. Then came the infamous leap in September 1752, where Wednesday the 2nd was immediately followed by Thursday the 14th, omitting 11 nominal days to bring British time into alignment with Western Europe. The Calendar New Style Act 1750 meticulously specified that while these dates were being skipped, no natural days were being lost, a legal nuance designed to prevent people from being cheated out of wages, rent, or interest, a logic that explains why the British tax year still begins in April to this day. This shift created a lasting archival seam across the American colonies, complicating historical records where old-style and new-style dating often collide. While the legendary slogan, "Give us our 11 days," remains a cinematic symbol of populist anger at elite meddling, historians like Robert Poole suggest the calendar riots may be more of a cultural myth born from 18th century satire, like Hogarth's paintings, rather than actual documented violence. Ultimately, 1752 demonstrates that while modern states regulate time through law, the act of changing the calendar exposes a raw nerve, proving that time only feels like a natural constant until the government changes the rulebook, making the abstract suddenly feel very personal. The international date line is one of those things that sounds official, like it must be carved into the ocean floor, but it's not. It's an imaginary boundary that separates one calendar date from the next, and it exists because time zones have to close the loop somewhere on a round planet. NOAA describes it as a line of demarcation between two consecutive calendar dates, and Britannica is just as blunt. It's an imaginary line from pole to pole, corresponding mostly to the 180th meridian, but it bends because people live on islands, because borders matter, because nobody wants their community split into today and tomorrow, depending on which side of town you're on. And once you accept that it bends, you also accept something that's quietly wild. It can be bent on purpose. When you cross the date line westward, you add a day. When you cross it eastward, you subtract a day. That's the basic travel rule, and it's why you can land before you took off if you're chasing the calendar the right way. But the story gets more human when it's not a traveler crossing the line, it's the line crossing a country. Samoa and Tokelau did that in 2011, and the U.S. Department of State's Office of the Geographer states it with zero drama. At midnight on December 29, 2011, Samoa and Tokelau moved from the eastern side of the international date line to the western side, losing December 30th and proceeding to December 31st, specifically to harmonize business hours with trading partners in Asia and Oceania. In plain language, the government chose to be on the same weekday as Australia and New Zealand, and it paid the one-time cost. Friday was canceled. The reporting at the time made it feel very everyday, almost funny, Like, okay, sorry, you don't have a Friday, but also you still have to get paid. For example, The Guardian noted that workers scheduled for the non-existent Friday were to be given a full day's pay anyway, which tells you exactly where the pressure was: fairness, labor, normal life. And Samoa isn't the only case. Kiribati did a related move in the mid-1990s so the whole country would share the same date. The U.S. Department of State background note on Kiribati says that on January 1, 1995, Kiribati unilaterally moved the international dateline to include its easternmost islands and make it the same day throughout the country. National Geographic Education uses Kiribati as a clean teaching example of why the dateline bends. Hawaii and Kiribati sit under similar longitudes, but because the dateline swings around Kiribati, they're a day apart. So the dateline ends up being a history lesson in disguise. It shows that what day is it is partly astronomy, sure, but it's also economics and governance and social convenience, and sometimes you can literally hear the decision in the way people explain it. We needed the same work week as our partners, not the Earth demanded it. And for an American audience, there's a nice grounded geographic reminder in Britannica's description. The line deviates through the Bering Strait area and bends to keep the Aleutian Islands with Alaska, which is a quiet example of the same principle. Don't split a community if you can avoid it. The international dateline is how civil time handles the planet's shape, and because it's a convention, it can be renegotiated. That's why a missing day can happen without any calendar reform at all, without any new leap year rule, just by changing which side of the line you want to live on. Up to a point, it was tempting to treat Earth's rotation as the clock, because it's the big, obvious cycle, day after day, and for most ordinary needs, it works. But once you push for precision, navigation, radio, satellites, networks, you run into a blunt fact. Earth's rotation is physically meaningful, yes, and also a little restless. It drifts and it wiggles, and it won't hold still just because humans want clean arithmetic. So the 20th century does something kind of bold. It flips the hierarchy. Instead of letting the planet define the second, we let an atom define it. In 1967, the SI second was redefined in atomic terms as 9,192,631,770 periods of radiation tied to a specific transition in cesium-133. That's the moment the tick stops being borrowed from the sky and becomes something you can reproduce in a lab, day or night, winter or summer, cloudy or clear. From there, the world builds a global atomic backbone, International Atomic Time, TAI, computed by the BIPM using clock data from many laboratories and time links. It's continuous. It doesn't jump around for Earth's convenience. It just keeps counting SI seconds with a steadiness that the rotating Earth can't naturally match. But civil life still cares about the sun in a quiet way. People expect noon to be near sun overhead. They expect dates to stay tied to Earth's rotation, at least loosely. So we end up with a compromise timescale, UTC. Since 1972, UTC is basically atomic time with occasional 1-second steps, leap seconds, inserted to keep civil time from drifting too far away from Earth rotation time. An ITUR explainer puts it simply, UTC is obtained from TAI plus leap seconds, and that leap second system begins in 1972. NIST says the same thing in its own blunt operational language. Leap seconds are used to keep the difference between UT1 and UTC within plus or minus 0.9 seconds, And it even lists the first leap second as June 30th, 1972, which is a nice "this is not theoretical" anchor. Now we have to name the other side of the relationship, UT1. UT1 is, in effect, Earth rotation time. IERS defines UT1 as the rotation angle about Earth's pole, and it distributes UT1 minus UTC values in its bulletins so the world can track how far the planet has wandered from the broadcast civil scale. So by the late 20th century, what time is it splits in a way that would have sounded strange in 1400. UTC is the smoothish civil standard tied to atomic seconds, and UT1 is the sky-facing measure tied to the rotating Earth, and the modern world lives in the gap between them. The gap is usually small, but it matters because systems that want continuity hate jumps, while societies that want the calendar to feel solar hate drift. Leap seconds are the clumsy bridge, and they exist because we decided atomic clocks should run the show, but we still want the show to resemble the old sky-based schedule. Leap seconds are the tiny fix that turns into a real-world headache because they're not about romance or philosophy. They're about keeping civil time from drifting too far away from how Earth actually rotates. Our everyday timescale, UTC, is built on atomic seconds that tick steadily, and Earth rotation time, UT1, is tied to the planet's spin, which is a little irregular, so the system compromises. When UTC and Earth rotation start getting too far apart, the world sometimes inserts 1 extra second into UTC to pull it back closer to the sky. NIST explains the idea in plain terms. Leap seconds exist so UT1 and UTC stay within about 1 second of each other, and when a positive leap second happens, you can see a weird timestamp like 23:59:60 right before midnight rolls over. That 23:59:60 is the part that makes engineers groan, because lots of software quietly assumed every minute has exactly 60 seconds, always, and then UTC shows up with a 61-second minute. Nothing is wrong with physics, but plenty can go wrong with systems that were never tested for it. The official referee here is the IERS. It monitors Earth rotation and announces leap-second decisions in its Bulletin C on a regular schedule, even when the message is basically "no change this time," which is boring in the best way. If you want one concrete anchor without drowning in numbers, the most recent leap second was added at the end of December 2016, and IERS Bulletin C52 is the formal announcement that spelled out the extra second at the end of that day. In the U.S. context, the concern was practical enough that CISA published guidance ahead of that event. Test your systems. Know how your time sources behave. Don't improvise at the last minute, because failures weren't hypothetical in modern networks. And because everyone hates a sudden 1-second step, some operators use workarounds that keep their internal clocks continuous. Google, for example, documents a leap smear approach that spreads the extra second gradually across a window so systems don't see a hard jump. So leap seconds sit in this awkward middle zone. They keep civil time politely near the sky, but they can be technically disruptive. And over time, the debate has shifted from "is this conceptually correct?" to "is this worth the operational risk?" That shift is now official policy territory. The CGPM's 2022 Resolution 4 points toward changing UTC so it can remain continuous for at least a century, and it calls for a plan to implement a new, larger allowed UT1-UTC difference by or before 2035, meaning leap-second-style steps would likely become rare or stop for a long stretch, with details still being worked out. By now, you can feel the basic tension without me selling it. Civil time wants to be smooth and boring. Earth rotation refuses to be perfectly smooth, and modern infrastructure is allergic to surprise 1-second jumps. So the direction of travel, officially, is toward a more continuous UTC. In 2022, the General Conference on Weights and Measures adopted Resolution 4 that points straight at a change. Increase the maximum permitted value of UT1 minus UTC so UTC can remain continuous for at least a century, and prepare a plan to implement that new maximum by or before 2035. The ITU's own discussion document on the future of UTC treats this as an active, open process. CGPM sets the timeline and a future limit, stakeholders keep talking, and the technical work is still about how to do it without breaking services that depend on UT1 minus UTC being small and familiar. If you want the mood check for where we are right now, it's almost anticlimactic. Leap seconds have already been absent for a long stretch. The U.S. Naval Observatory's leap second page states there will be no leap second at the end of December 2025, and it also notes the last leap second was introduced at the end of December 2016. IERS is still doing its job. Bulletin C remains the official announcement channel, with the latest issue page updated as recently as July 2025, so the machinery is running even when it has nothing dramatic to announce. So what changes if the world widens the tolerance and stops inserting leap seconds for a long time, maybe a century? The good part is obvious and kind of boring, which is exactly what engineers like. Fewer discontinuities, less risk of time sink incidents, less what does my system do with 235960. The trade-off is also plain. UTC would slowly drift away from UT1, meaning clock noon would gradually separate from sun near the meridian noon. Not quickly, not in a way you notice in a week, but steadily enough that future people will have to decide what they care about more: continuity for machines or tight alignment between civil time and the rotating Earth. And that doesn't mean astronomy or navigation gets lost in the fog. It means those fields lean harder on Earth orientation products and explicit corrections, UT1 UTC values, DUT1 broadcasts, software that knows when it needs Earth rotation and when it needs a uniform atomic scale. Basically, you stop pretending one timescale can satisfy every purpose. The long-range cultural consequence is the part that sounds sleepy until you really think about it. If you let the gap grow for many decades, eventually you're talking about minutes, later hours, and then somebody, someday, has to pick a new kind of calendar patch, maybe bigger and rarer than leap seconds. People toss around ideas like leap minutes or scheduled adjustments, but the exact design is what the 2035 planning window is for, and it's why the official documents keep using words like continuity, acceptability, and review period. So the ending of this is not a punchline, it's a fork in the road with paperwork attached. We started with days that vanished because humans edited calendars and maps, and we end with a future where the editing may shift from add a second sometimes to allow a slow drift for a long time, and the real historical question becomes, again, the same one we've been circling. What does society want time to be for, and how much mismatch with the sky is it willing to tolerate to keep the machines calm? Thank you so much for watching our video and supporting the channel. See you in the next episodes, and good night.